What is the integral from 0 to pi over 2 sine cubed theta cosine cubed theta d theta? And we have some options, 1 over 24, 1 over 12, 1 over 6, 1 over 4, and 1 over 3. It's reasonable, by the way, that the answer should be somewhere between 0 and 1, because sine cubed theta cosine cubed theta is somewhere between 0 and 1 when we're between 0 and pi halves. All right, do we have an answer? Does someone work this out? B? Yes, it is B, 1 over 12. Now this is a case where they're both odd exponents. That's a great case to be in. Now when they're both odd, you get a choice. You can pull off a sine towards the end, or you can pull off a cosine towards the end. Now there's a little piece of advice here in the corner. If you can pull off either, then pull off the cosine. That's my piece of advice. Now, why? Well, that's what we did here. And the reason we're pulling it off is ultimately we're thinking that's going to become our du term. And we're going to rewrite everything in terms of, in this case, in terms of sine. So we're replacing the cosine with 1 minus sine squared. Now, the reason why I prefer to pull off the cosine is if we make the substitution u equals sine theta, the derivative is cosine theta. If we pulled off the sine and made the substitution cosine, we'd still get the same answer. It would all work out. But if you put u equals cosine theta, what's du? Negative sine theta. And those minus signs are pesky. And so that's why I recommend pull off the cosine. So you have one less thing to worry about. So okay, so we pulled off the cosine. Everything becomes in terms of sine. We make the substitution. We have a polynomial. We integrate. We evaluate. Life is good. All right. And of course, because this is a definite integral, update your bounds. You never have to go back. We didn't have to say, oh, let's go back to theta. No. With definite integrals, once you've updated your bounds, you never go back. So that's our warm-up problem. Any questions on this one? Now, someone did come up afterwards and ask a question. And it's related to this. So we were talking about, well, we have this sort of notion that we could like trade a cosine squared for a sine squared. Or we also have this notion we can replace a cosine squared with 1/2 times 1 plus cosine 2 theta. And so the question is, how do I know when to do what? And so we think about our philosophies, like what's our goal? We want to simplify. And so we're trying to make things simpler. Now there's another thing, do the insides match? So here, when I'm thinking about order reduction, I have to say at the end of the process, all the insides have to look like 2 theta. If they're not the same, then that's bad, because you really have to make sure all of your insides match. So when we do order reduction, everything has to become double the angle that we started with. So that's one way you can test. It's like, okay, if I go through order reduction, will everything at the end be double what I have right now? If not, I probably need to think about doing some kind of a trade. Because with trades, the insides stay the same. When you do order reduction, the insides change. All right. So, our thought for today. The only real mistake is the one from which we learn nothing. And there's sort of one of our philosophies which keeps coming up again and again is don't be afraid of mistakes. Don't let mistakes stop you from trying something. Don't let the fear of being wrong stop you from being right. A lot of people say, look, I'd rather not even try than try and make a mistake and try and be wrong. It's important to be brave enough to say, I will try something. And if I make a mistake, that's okay. I'll learn from it. It's preferable not to learn from exams, but you have to learn sometime. So don't worry about making mistakes. Just worry about not learning from them. The goal is not to be perfect, but to be better. And it's a process, something to strive for. All right, our goals for today. We still have some things to talk about for trig integrals, so we're going to do that. And then we're going to do more practice. So this is in some sense a catch-up day. And one of the things that we should get to, we may or may not, but we're not learning new techniques today. We're practicing what we've learned. And just noting, there are cases where we can take these ideas and apply them to some of the things we've already learned. So these techniques that we're learning exist for a reason, because they rose in various applications. And hopefully we'll have time to see that. All right. We stopped here last time, and I want to make sure we cover this. If an integral has something in the form 1 plus or minus cosine, 1 plus or minus sine, secant theta plus minus 1, in a pesky place, something annoying. So inside a square root, inside the denominator, then what we can do is we can use multiplying by the conjugate to help us simplify it. And so in particular, we can help get things outside of a square root, or we can help make the plus or minus that's in the denominator go away. Pluses and minuses, there's good pluses and there's bad pluses. We're going to talk about this next week. There's places where you like the plus and there's places where you don't. And so this is one way to sort of say, well, can we change the game a bit? All right, now why do we multiply by the conjugate? Well, because we have our Pythagorean identities, and that helps us move forward. So here's an example. An example will help illustrate. Integral from 0 to pi over 4, square root 1 plus cosine 4x dx. All right, right now, not looking very hopeful. But there's an idea. Well, it's over here. We have a 1 plus a cosine inside a square root. So we'd like to say, well, we'd like to get something outside a square root. So let's apply this idea. All right, so we have, this will be the integral, 0 to pi over 4. And we'll just do it all inside the square root. Now, when you multiply by the conjugate, what do you need to be careful of? Or what do you need to make sure to do, is another way to phrase my question. I know, a very vague question. Any thoughts? We multiply by the conjugate. What do we need to make sure happens? Well, we're flipping the sign in the middle, but what else do we need to do?
Multiply by the top and the bottom.
Multiply by top and the bottom. Why do we need to do this?
It's the same as multiplying by 1.
Multiplying by 1. We have to make sure that we're still doing the same function. Our goal is not to change the function. Our goal is to express the function in a different way. So it's still the same function, just has a different expression. Okay, so thinking of this as 1 plus cosine 4x, we'll think of it, we'll throw a 1 there, because we're going to multiply top and bottom. We'll do it inside the square root. It's a big square root. There's enough space. All right. So, upstairs, 1 plus cosine 4x times 1 minus cosine 4x becomes 1 minus cosine squared 4x. And the bottom becomes 1 minus cosine 4x. And I know right now it doesn't look better, but let's think through the process. 1 plus cosine 4x, there's not a lot we can do with that. 1 minus cosine squared of 4x, there is something we can do with that. What happens to the upstairs? Yeah, so what's going to happen is that this part upstairs, that's going to be a sine squared of 4x. And notice, sine squared has a square. And we're taking a square root. And we're like, nice. So if we do that, we'll think of taking the square root on the top. So we have 0 to the power of 4th sine of 4x upstairs. Now downstairs, I can't do much, so I'm going to leave that inside the square root. So square root of 1 minus cosine 4x. All right. So using conjugation, we have now successfully rewritten our function in a different way. The question, is it better? Has our situation improved? Yes? How has it improved? What can we do? We can do a straightforward substitution. This part that we've introduced upstairs is now the derivative of something. So in particular, we say, well, let's set this term to be u. So we have u equals 1 minus cosine of 4x. du, well, that'll be the derivative of cosine 4x. Well, there's a minus there. Derivative of cosine is going to be another minus sine of 4x. Anything else? Put in a 4. Anything else? dx. Oh, I don't have quite enough room, but I'll pretend like I do. All right. So we could also write this as 1/4 du is sine of 4x dx. All right. We're close. We're close. Okay, so let's now update. Let's start with the bounds. When we plug in 0, what do we get? 1 minus cosine of 0. 1. Because cosine of 0 is 1. 1 minus 1 is 0. Okay, plug in pi over 4. 4 times pi over 4 is pi. 1 minus cosine pi. 2. Cosine of pi is negative 1. 1 subtract negative 1 is 1 plus 1. Yes? I see some skepticism. Ah, you're right. It's 1 minus 1. 0. Good. Thank you. I make mistakes. Aha! I've learned. Good. Good. I've learned from my mistakes. Okay. 0 to 2. The sine of 4x dx, that's a 1/4 du. And what else do we have left? U to the minus a half. All right. Well, we'll now integrate. So that's 1/4. Add 1 to negative a half. You get 1/2. And multiply by the reciprocal. Evaluate from 0 to 2. So we really have 1/2 in front. When we plug in 2, we get 2 to the 1/2, which is square root of 2. When we plug in 0, we get 0. So our answer is 1/2 times square root of 2. All right. Any questions? Okay. Good. That means you're pros at this kind of thing. So you're ready. I promised you a multiple choice. So here you go. Find the integral of secant theta times the square root of 1 plus secant theta d theta. So do we have the answer? A, B, C, D, or E? I mean, we probably know things it's not.
There's no option.
There's no option?
Yeah, you actually can't do it.
That's not an option. It is one of these 4, 5. It's one of these 5. I promise you, it is there. Now, can I ask you, what does your answer involve?
Sec theta minus 1 plus c.
Oh. A lot of people's answers probably involve a secant minus 1. What do we not have? We don't have any secant minus 1s. Oh my goodness, what happened? How do you replace the secant minus 1 inside a square root? We do conjugation. The conjugation's so nice, we did it twice. The answer is D. Okay. So, all right. Well, so one tricky thing here is the way this problem asked. You had that square root of 1 plus secant theta. It really was better if it had asked secant theta plus 1. So that's one thing you had to be careful about. But most people have the right idea. Conjugation, substitution, and we have an integral, which isn't too bad. So I suspect a lot of people did pretty well getting to here. But the problem is, in multiple choice, you have to figure out which one matches. And so in this case, it was like, well, all of these are in terms of secant plus 1. This is secant minus 1, so use conjugation a second time. All right. This was a challenging problem. I will be honest with you. I knew it would be challenging. An algebra question. Well, you can change the order of secant 1 plus secant theta to be secant plus 1. And so you want to put it in the order that's most convenient. All right. Well, now that we've had good practice for today, the last set of trig integrals that we will want to be able to attack are integrals of the form secant to a power, tangent to a power. Now, this behaves a little bit differently than sines and cosines, but fundamentally, at the end of the day, it's the same kind of process. Can I trade secants and tangents in a way that I end up with something that I like? Now, there are 3 cases, 2 of them we like. The first case says I can move secants and tangents around. So in other words, I can trade a secant squared for a tangent squared or vice versa. I can pull off a secant squared at the end, and everything else is in terms of tangent. And if that's the case, we're like, yes! Because we can make a substitution, u equals tangent, du equals secant squared. Or maybe we can pull off a single secant and a single tangent. So we have a secant tangent at the end. We pull that aside, and we say everything else looks like secant. And we say, great. And then we set u equals secant and du equals secant tangent. And when does this not work? Well, if it doesn't work for one of those 2 cases, it means that what we have essentially looks like secant to an odd power. This is ugh. We do not want this. And now, usually when we end up with that on exams, historically, 100% of the time, we say, oh, and here's the formula for it. And we'll explain how you do that in a few minutes. But the other 2 are more straightforward. So let's see by example. Find the integral of tangent cubed secant to the 4th theta d theta. Now, when you see a problem that involves tangents and secants, there's sort of a mental computation that goes on in your head. You say, let me pull off a secant squared, and let me pull off a secant tangent. So let's do both. So if I pull off a secant squared, I have tangent cubed theta, secant squared theta, secant squared theta d theta. So this is sort of an internal computation. And we're going to look at that. On the other hand, if we pull off a secant tangent, we'd have a tangent squared theta, secant squared theta, secant theta, tangent theta. So this is, in our mind, we think about these 2 scenarios. Now we say, are either of these a good situation? So if I'm thinking of pulling off a secant squared, what do I want this to look like? If a secant squared's on the end, what do I want here? Wants tangent stuff. So I asked myself, can I do a trade? Can I trade secants for tangents here? So I look at the power of secant. Is that an even power? Yes. And we're like, yes, we can make a trade. So this becomes the integral. We're going to do tangent cubed. That stays there. Secant squared becomes what? What's our identity? Tangent squared plus 1. And then we have our secant squared theta d theta. Now we make our substitution. U equals tangent. du equals secant squared theta d theta. So we really have the integral of u cubed, u squared plus 1 du. And now we have a fairly straightforward algebra type integral. All right, well, no surprises here. We distribute u to the 5th plus u cubed. We integrate 1/6 u to the 6th plus 1/4 u to the 4th plus c. Are we done? Got to get back into where we started. So we replace u by tangent. So this is 1/6 tangent to the 6th theta plus 1/4 tangent to the 4th theta plus c. And there's our answer. Okay, now that's if we went down that route because it worked out. If we pulled off a secant squared, we're like, hey, we have the ability to write everything else in terms of tangents. But now let's look at what would happen in the other situation. We pulled off a secant tangent. And now we ask what? Well, if we have a secant tangent, we want stuff with secant. So can we make it all in terms of secant? Look at your tangents. Can you make your trade? You need tangent to an even power. Do we have that? Yes. So I say, great. So we're going to replace the tangent by something times secant squared. And then we'll still have our secant theta, tangent theta d theta. What does tangent squared get replaced by? Secant squared minus 1. All right, let u equal secant. du equals secant theta tangent theta d theta. And now what do we have? U squared minus 1 times u squared du. I'm missing a secant. Ah! Wait, am I? Yes. Yeah, these are cubes. Thank you. There we go. That's an easy one to fix. All right. Well, again, algebra, a little bit of deja vu. It feels kind of similar to what we did before. So we get 1/6 u to the 6th minus 1/4 u to the 4th. We're like, whoa, minus. Well, but of course, do the same thing, substitute. So we get 1/6 secant to the 6th theta minus 1/4 secant to the 4th theta plus c. So that's our answer. Now, there's kind of a mystery here. We have two answers, but they don't look the same. What does that mean? Well, they are the same. Up to what? Plus c. So that's one of the things with trig integrals. Sometimes you have multiple ways to approach the integral. So you can have multiple ways to express your answer. But you could unravel and spend a few 15, 20 minutes to get from one to the other. Not worth it, not worth it.
Would this be like a word problem or like a multiple choice problem?
I don't know. Yes.
Yes.
Yes. All right. So that's the good cases. Are we ready for the UG?
Yes.
Bring on the UG. So, there's a nice fun fact. The integral of secant to the n of x is 1 over n minus 1 secant to the n minus 2 of x tangent of x plus n minus 2 over n minus 1 times the integral of secant to the n minus 2 of x dx. Let me preface what we're about to say here with the following warning. You do not need to memorize this. You do need to be able to derive it. We do not expect you to memorize this. Okay, so let's derive it, because it says show. Okay, so any thought on how we might be able to show this? This is why it's fun. All right, so here is what we're going to do. We have secant. Is there any case with secant that we like when it comes to integration? We love secant squared. We can integrate secant squared. So, idea. Let's put this into two pieces. Something we can't do and something we can. And you're like, uh-oh, I see where you're going with this. We're going to do integration by parts. That's going to be our dv. That's going to be our u. Now, we can integrate secant squared. Integral of secant squared is tangent. Derivative of secant to the n minus 2 is, I did not give myself enough room. N minus 2 comes down. Secant to what power? N minus 3. Anything else? We're doing chain rule, so we have to multiply by the derivative of secant, which is secant tangent. And dx. Or, if you like, n minus 2, secant to the power n minus 2 of x, tangent of x, dx. All right. The good news is this is a computation you only have to do once in your life, so today's the day. But at least you'll know I did it. You can tell your grandkids, I did it. I remember the day. It was a warm spring day. Warm-ish spring day. UV, secant to the n minus 2 of x, tangent of x. All right, so UV minus the integral of v du. So we have an n minus 2 secant to the n minus 2 of x, and a tangent x and a tangent x makes this tangent squared of x dx. So here's our v du. Okay, good. We're halfway there. Now, the good news is no more integrals are going to have to be involved. The rest of this is moving stuff around. What do we have here? I'll give you a hint, I'm pointing at it. Tangent squared. What can we do with tangent squared? Becomes secant squared minus 1. So, we still have our term here, secant to the n minus 2 of x, tangent of x, minus the integral n minus 2, secant to the n minus 2 of x, times secant squared of x minus 1. Which we can distribute here and then pull apart into two integrals. So if you do this, you get secant to the n minus 2 of x, tangent of x, minus, I'll pull the n minus 2 out because it's a constant, secant to the n minus 2 times secant squared makes secant to the n of x. And then there'll be a plus, pull out the n minus 2. And then you have secant squared to the n minus 2 times 1. So that's secant to the n minus 2 of x dx. Okay. Whew. What can we do now? Where did we start? Secant to the n. What do we have? Secant to the n. So we started with the integral with secant to the n, and now we have an integral with secant to the n. So we're going to move this across. And we're just going to say, let's join you with your friend. So in other words, we have 1 secant to the n over on the left-hand side. Here we have n minus 2 secant to the n with a minus. So when we move it across, that leaves us with n minus 2 plus 1, which is n minus 1, integral secant to the n of x is secant to the n minus 2 of x times tangent of x plus n minus 2 integral secant to the n minus 2 of x dx. We're almost there. We almost have secant to the n. What do you need to do to finish it up? Get rid of the n minus 1. So the integral secant to the n of x dx is 1 over n minus 1 secant to the n minus 2 of x tangent of x plus n minus 2 over n minus 1 integral secant to the n minus 2 of x dx. Okay. Whew. We finished the show. Now, any questions? It's a little bit unusual. It's one of those things where you do integration by parts and rearrange.
So would that just be the case for anything that would just be if it's odd?
Well, this works for even or odd, but it's only useful for odd. So there's nothing here where we assumed even or oddness. But essentially what it says is, I can switch out integral of secant to the n with integral of secant to a smaller power. So it's like, that looks easier. So that's the goal. Okay, so there is this other part, secant to the fifth. So let's follow what this says. So the integral of secant to the fifth of x. So n equals 5. So I'm going to come here. Everywhere we see n, I'm going to put it in a 5. So 1 over 5 minus 1, that's 4. Secant cubed of x, because that's 5 minus 2. Tangent of x. And then we have 5 minus 2, which is 3. 5 minus 1 is 4. So plus 3/4 integral secant cubed of x dx. So we apply the rule once. Are we done? No, because we still have an integral. But what we've done is we traded a hard integral for a slightly less hard integral. How does one integrate secant cubed? We apply the formula again. So we have secant cubed of x, tangent of x. We're just copying that down. We have a 3/4, and because we love points, we put a big parenthesis. And now we apply the formula a second time, but now with n equals 3. So we get 1 over 3 minus 1, so that's a half. Secant of x, tangent of x. Then we have 3 minus 2 over 3 minus 1, so that's a half. Integral secant of x. Okay, now are we done? No, because we have the integral of secant of x. And how do we integrate secant of x? We just know that one. It's on our formula sheet. So don't forget to distribute the 3/4. So we get 1/4 secant cubed of x, tangent of x, plus 3/8 secant of x, tangent of x, plus 3/8, and the integral of secant involves a natural log. Secant of x plus tangent of x. And of course, plus c. And now you sort of say, okay, I get the UG. It's a reasonable UG. All right. So, in the last few minutes, just a quick reminder, integrals here have applications. And so while we're learning techniques of integration, they tie back to helping us answer applications. So we can do applications that we couldn't before. And so when we do things like integration by parts, things like surface area, moments, shell method, they tend to involve like x times something. And that tends to be a pretty good candidate for integration by parts. Trig integrals arrive in a lot of places, but are really common when we talk about polar coordinates, because we often phrase things in polar coordinates. And so remember, we're learning all these techniques. We've said this before. It's not enough to know how to apply a technique. You also need to know when. So let's at least set up this problem. Find the volume when the region 0 less than or equal to y less than or equal to secant squared x for 0 less than or equal to x less than or equal to pi over 4 is spun around the y-axis. So if you sketch this, so we'll be a little bit sketchy here. There's pi force. Here's your region. We're spinning around what axis? Y-axis. The y-axis. So we're spinning this way. What technique should we be using? Well, let's assume we do how the problem suggests it's presented. So it presents itself in terms of x, functions of x. That means vertical slicing. If we spin this way, what are we making? Shell. So y-axis would be a shell method. And we say, hey, we know how to do that. We have volume is the integral a to b 2 pi radius, height, width. So for us, a and b, 0 to pi over 4, 2 pi, radius, x, height, secant squared of x, width, dx. What's your technique? This is a by parts. What do? Well, your two candidates are x and secant squared x. Which one should you have be your u? Which one do you want to have be your dv? It's not always obvious, so I don't be like, aha, it's obvious. So in this case, x is a good candidate for u, because if you take the derivative of x, what does it become? 1. That's a lot easier to work with. And can you integrate secant squared? Yes. Now, we won't carry it out. But what if the problem had said around the x-axis? Then what would have happened? So then, the formula is integral a to b pi radius squared, because it's disk method, width. So integral 0 to pi over 4 pi. Radius is still that length. So what's our radius squared? Secant to the 4th. And our width is still dx. Now what technique do you use? Now this is a trig integral. It's a secant tangent kind of thing. In this case, talking about what we did today, what would you do? Pull off a secant squared, replace the other secant squared in terms of tangent squared, and you're off to the races. So, okay, so there are nice applications.